Okay, then I'd say we'll start this session. Welcome everybody to the session on parallel, distributed, and concurrent systems. We've got 3 presentations in this session, so we can take a little bit of time for each one of them and have plenty of opportunity to ask questions. For everybody that has a question, please feel free to write that up into the chat. Given the number of attendees, we may actually ask people to phrase their questions directly. I think that's always a bit more personal than me reading a question from a chat. Anas Nadim is the first presenter. So could you please share your screen, Anas, and then it's all yours and ready to go.
All right. Thank you, Jean, for the introductions. I'll go ahead and share my screen. And I hope everybody can see it now. All right.
Yep, we can see that.
Awesome.
You can make it a little bit bigger. Yep, that's good. Great.
Okay, awesome. So should I start?
Yeah, go ahead.
All right. Okay. Hi, everyone. My name is Anas Nadim, and I'm a graduate student at North Dakota State University in the Department of Computer Science, and I'll be presenting our work titled A Case for Microservice Orchestration Using Workflow Engines. So before we dive into the presentation itself, let's discuss architectures and the need of microservices themselves. The first architecture or the predominantly used architecture in the past as well is the monolithic architecture, which involves having everything in the same place. The communication between the components happen to be local, and the pros of this type of architecture involves easy to debug faults through simple logs and breakpoints. However, it involves having tightly coupled components, and the application itself is very heavyweight and difficult to maintain. Moving on to microservices, it gives us the leverage of breaking down the bigger system or the monolith system into smaller independent applications that run in independent processes, which in turn are loosely coupled and scalable and distributed in nature. Which means that one microservices or the same microservice can have multiple copies of itself, and in case one of the copy fails to execute, the traffic can be redirected to another copy of the same microservice, and the system can continue executing even if some of the microservices fail. Now, a single microservice interaction or the process can span across multiple microservices. Also, the deployment of microservices may also be distributed over multiple machines and might also be based on different geological regions. So below you see an example of such an interaction. The interaction between these services, there are like 3 services involved in this process. The details of what happens in this process is not relevant, but we can see that they communicate over the network, and there are like multiple microservices involved in the same process. The motivation behind our work is simple. First, since microservices are complex due to their dynamism, it's important that we discuss ways to make it easier to debug them or like visualize them. And understanding the interactions between microservices is troublesome. So therefore, our work here intends to explore ways to make this interaction simpler first, and secondly, make the ways for debugging easier and efficient. So normally there are 2 interaction modes for microservice communication, the communications that we just saw in the previous screen, which is over the network. The first one is the orchestration mechanism, where there is a central brain or a central coordinator that directs the interaction between the services, as seen on the left, and choreography, in which the services, in which the communication or the networking between the services is directed by the services themselves or through events. Now, historically, choreography has been more prevalently used because the implementation of microservices in a choreography-based techniques is generally easier because it mostly follows an event-driven paradigm. So services can be like just plugged in and played. However, the benefits come at a cost, and we believe that there is no such thing as free lunch. When in a choreography-based approach, when the number of microservices increase and the interactions increase, technical debt is seen to have been embedded inside the business processes, resulting in the debugging process to become very complicated. Therefore, in order to solve these challenges, we tend to explore the following using the following contributions in our work. First, we poured the largest benchmark available to the best of our knowledge to orchestration, which is priorly implemented in a choreography technique to observe the benefits of the latter. Then we highlight the practices of debugging 22 injected bugs in the original benchmark system, and then we compare results with the benchmark system, which highlights debugging times over the 22 injected bugs. So first, let's discuss what the framework that we're going to be using. So workflow is a term synonymous for business processes or a business process or interaction. On the right, you can see the same microservice process that we had in the prior slide, and we're just calling it a ticket constellation workflow because it involves the interaction between microservices that cancels a ticket in the benchmark system, actually. And workflow engines are basically low-level distributed, are basically frameworks that enable a user to, by themselves managing the low-level distributed programming and allows the developers to focus on implementing business logic. Examples of workflow engines are the Netflix Conductor, Apache Airflow, Uber Cadence, and Temporal. In this work, we chose Temporal. The reasons for this choice was twofold. Number one, it has an easy-to-use programming language-based API. And second, it has an extensive framework support, which might come in handy in our work, which we believe came in handy. Okay, and now a little detail about the benchmark system itself. The benchmark system is called Train Ticket. It is, to the best of our knowledge, the largest publicly available, which almost 30 microservices, and it replicates faults from 22 industrial fault cases. We map all these faults into code recognizable by temporal orchestrator and then systematically debug them. So one such, the same interaction that we discussed in the prior examples, we map it into temporal framework. We discussed the exact steps that were involved in mapping this and the practices that we followed to map this in detail in the paper. But for the sake of it, for the demonstration purposes, here is how the process looks like after mapping it into a workflow engine. After mapping these fault cases, we had a user who had 2 years of industry experience, no prior knowledge of the faults, and who went through elementary training of temporal framework and the support available for debugging in itself to debug these 22 fault cases. And then finally, we compared these results with the benchmark study results, which will be discussed later in the presentation. So moving on to the practices that were involved in the debugging process, the first one was problem-based construction, which involved collecting stack trace and visual trace graphs from temporal web UI, which was a part of the temporal framework itself. Then the second step was the identification of fault symptoms. In this step, we actually had a minimal environment setup of the microservices involved in the process, and then we compared the results of the expected results with the ones that were the actual results to see what could be possibly the symptoms of this fault. And then third was the actual fault diagnosis steps, in which we hypothesized the fault location, again using the trace and the visual trace collected in the first step. Finally, we used solution generation and verification step, which involved the resolution of the issue and verification of necessary test cases to see if the fault has been resolved. Now, in gray, we can see the results from the original benchmark study, And in blue, we can see the results that were recorded by us in the orchestrated version of the benchmark system. And we can clearly see that the time taken by the user in the orchestrated approach was basically lesser than the time taken by the users who actually debug the benchmark system in a choreographed approach. Now, this leads to the conclusion that orchestration is actually advantageous over choreography as it makes debugging easier and faster. So, in this presentation, we actually ported train ticket benchmark system to a fault oblivious stateful workflow engine. We replicated the fault cases to assess the time taken to debug in orchestration rather than the choreographed approach in the original benchmark study. And for future work, we plan to continue the study with more participants. We plan to port more benchmark systems to temporal and study performance on availability issues. We also plan to use other DSL-based engines, especially the ones discussed in this presentation earlier, including Netflix Conductor, Uber Cadence, and vice versa, to study if they have similar impacts on helping with the debugging times and see their response and the feedback. That concludes my presentation, and I'll be happy to take any questions.
Thank you, Anas. Do we have any questions from the audience? We don't have any in the chat. Then I may start with a question. What assumptions do you make about the logging facilities of these microservices for your work? Is there anything particular you need, or doesn't it really matter?
It doesn't really matter. We're basically for the logging, we mostly rely on the framework itself. So mostly the frameworks they support. The framework that we were looking at, they supported these kind of log and trace analysis. So we actually don't really require any standards to be met. It was just like since it was a case study, our user it was totally based on the perception of the user and what the output of the log was. So not necessarily there were no required standards.
Now, the moment you have a service running somewhere else, right? There is always the possibility that through network communication, something can go wrong. Do the bugs that you looked into include latency issues?
Well, yeah, that is true. Obviously, the latency issues are under consideration, but we also noticed that these workflow engines, this framework technologies that we were using, they actually did handle these kind of issues themselves. Actually, they supported themselves. And in case there was a failure between, the communication of two services in between the process, they actually had the whole process resilient and fault tolerant. So in case of any failure between the communication, there were automatic retries and failure handling logic of that sort that was automatically handled for us. So yes, latency was an issue, but it was handled by the orchestrator itself. That's also one thing that we would like to highlight in our future work.
Now, if you would have to give one piece of advice to somebody that wants to develop a software solution using microservices with regards to debugging, fault detection, etc., what advice would you give them?
I would actually say it's a process. So microservices, they're complex when it comes to interactions, and there has to be a thought process that goes under it between how are you going to make the interactions between the microservices possible, what kind of hosting mechanisms are you going to use, how to make sure that you don't have any possibilities of a single point of failure. All of these questions need to be addressed while you're mapping your monolithic architecture into microservices, or you just have a microservice architecture right now, which is ready. So yeah, all of these questions need to be addressed.
Mm-hmm. Okay, does anybody else have a final question?
Maybe I have a question. Thanks for the great presentation, Anas.
Yes, please.
So you argue that orchestration might be superior to choreography, at least in terms of debug. But from a distributed systems perspective, when I see the orchestrator, what comes to my mind is, as you just mentioned, is single point of failure. Like it's a very central component of the system. So what are some effective approaches in the industry to deal with this and eliminate this single point of failure?
Okay, I was actually expecting that questions, and that is actually a great questions. So in terms of a single point of failure, it is true that since an orchestrator actually coordinates the interaction between the services, it's possible that the orchestrator might itself fail. So in the industry, a common practice is having a clustered orchestrator that actually replicates, all the logs or the events that are generated. So basically, these whenever an orchestrator is like going through a process, it basically has internal queues employed. So what happens is whenever a process is completed, only then the log is clear or the queue is cleared for that process. So as long as a process remains in the queue, the orchestrator doesn't take it out, and we can have multiple replicated instances or clusters of the same orchestrator. So that's one thing that actually gets rid of that single point of failure thing. Thank you for the question.
Thank you.
Okay, then. Well, thanks very much, Anas, for your presentation. And let's do a real or a virtual clap.
Thank you so much.
And I'll now handing over to Michael, who is our second presenter. So all yours, Michael. Hopefully sharing works fine.
Yeah, we'll see. Just gonna make this a little bit bigger. And, okay. Can everybody see that?
Yep, all good.
Okay. All right. So hi, everybody. My name is Michael McInnes. I'm a PhD student at Carleton University. My supervisors are Professor Olga Basel and Professor Michele Lanza. So I prepared this talk under the assumption that we were limited to 5 minutes. I didn't know that we'd have a little bit more time. So it is a little bit of a speed run of what we cover in our paper, Terminals All the Way Down, and the companion video. So we invite you to look at those for more detail. This talk is about using interconnected Unix terminals as the foundation for a new type of distributed and language agnostic development environment. Just so we're all on the same page, let's start with what's a Unix terminal. So the first Unix terminal was the teletype, and teletypes were replaced by video display terminals, and video display terminals were replaced by window terminal emulators. We claim, as others have pointed out, that window terminal emulators have been quietly evolving into a general support environment for text-based programs. In parallel with this evolution, numerous integrated development environments, or IDEs, have been created. And IDEs have converged on what some call a bento box model, where the screen is partitioned into rectangular areas. The layout is remarkably consistent given the number of IDEs. This is even more surprising when we consider that popular IDEs share little, if any, code. The code bases are increasingly large and complicated. This makes life hard for tool builders who must target each specific IDE. I don't think VS Code, shown here, was the first to include a terminal, and it probably won't be the last. Our approach can be summed up as flipping that inside out. What if instead of embedding a terminal in an IDE, we could bring IDE-like features to the terminal? There are many people working on bringing IDE-like auto-completion to the terminal. In the video, we show BPython, and here we see Fig. Popular Unix shells like Bash and Z shell have been leading the charge here. And in addition, the language server protocol has really leveled the playing field. We, of course, want to leverage all of that, but it isn't our main focus. The real power of window terminal emulators comes from the ability to juxtapose them. We want to go further and connect them. We think that many IDE features can be seen as the connection of juxtaposed textual windows. To name a few, being able to click on a file in a file tree or a listing and open or jump to that file. Similarly, being able to click on compiler errors or linter output and jump to the corresponding spot in a file. Being notified while editing a file what other windows are saying about that file. And even things like side-by-side diffs or interactive debuggers seem to fit this model. Juxtaposing window terminal emulators is already possible. We're working on connecting them and have started on an architecture to allow that. This is covered in more detail in the video and in the paper. One of the key things we're doing is baking in the idea that terminals don't have to be interacting with the local machine. The terminal has always been a portal. It can interact with the local machine, a remote machine, or a container. Enabling all of this is the ability to pass messages. We're currently encoding messages using an escape sequence known as a privacy message. Privacy messages are ignored by Xterm and all Xterm-like window terminal emulators, which is to say pretty much all window terminal emulators. With these messages, we can multiplex connections. This gives us the ability to create a component that's aware of what all the terminals are doing, as well as the ability to launch additional terminals as required, not only locally, but on remote machines and in containers. As we mentioned in the video, work on this has started. We can currently launch terminals locally, remotely, and in containers. All of these connected to local windowed terminal emulators. Our next step will be to recognize what some people call code addresses in output and see if there are existing terminal-based editors that we can easily extend as a proof of concept. We'd love for others to take a look. Please let us know what you think. Thanks for listening.
Thanks very much, Peter. Do we have any specific questions from the audience? If not, then I may start off with one. I'm playing slightly devil's advocate here, Michael. Mm-hmm. If I show a terminal to some of my students, they ask me, what is that?
Yes.
How do you, because they're so used to drag and drop, mm-hmm. How do you take the fear away from people going back to terminals, if I can put it that way?
Right. So one of the things that we're looking at is actually treating a terminal as more of like a textual widget in this framework. So it's just a place where you can display and interact with text. And so I don't think we're limited to the ways that people currently use it. Because I'm thinking specifically of a terminal-based editor. So what I'd really like is to see things to make it a little less alien. So, you know, Control-C to copy, Control-V to paste, that would be kind of nice, right? That's like the standard everywhere else. It would be kind of cool if that worked there too. So that's another thing that we're working on addressing as part of this.
Mm-hmm.
And I don't know if that answers your question.
I'm sort of trying to get a sense, who do you think will ultimately be the user of your work? Who do you want to, or who are you targeting?
I'm targeting me. So I've been developing for a professional developer for about 20 years, and I've used IDEs, but I tend to use the terminal a lot. And so it was, you know, how can I make this work better for me? And then there's others. I've encountered many others like me along the way, so it's for them as well. That's who we're looking at. And then I'd also like to see if we could, like you said, you know, people, if you show a student now a terminal, you know, they say, what is that? But I've actually been really impressed lately. We have, you know, students that join where I work, and a lot of the new students seem to actually be quite comfortable at a terminal. There was a time when they weren't, and they seem to be again. I don't know what's shifted, but it's encouraging.
Mm-hmm. Yeah, because I've come across a number of students, when you show them a terminal, they look at you with big wide open eyes. What is that? Yes. They may have never seen that. Mm-hmm. Because a lot of things can be done much, in my opinion, much quicker and more effectively in a terminal than if you have to start up another application, find the right menu, click on the right button, mm-hmm. and then you still have to type in some information that in a terminal you can do all in one go.
Yeah, and answering those like ad hoc questions are really easy to do usually from a terminal, right? If it's in another application, it sort of has to have already anticipated the type of question that you might want to ask.
Mm-hmm. Okay, I don't want to hijack the conversation here. Do we have any other questions?
If there are no other questions, I might go ahead and ask one. Thank you for the presentation, Michael. So recently I've seen a project, not really the same as yours, but they also proposed to extend terminal emulators, add new, graphical features and web integrations, basically make it more feature rich.
Okay.
And there seemed to be a community, probably not from everyone, but like a subgroup saying that terminals are not like this. They should be minimalistic. We value simplicity, and the complexity should be outsourced to other applications. So how would you counter this argument?
I don't think we're looking at changing that much of them would probably be my first response to them. We're looking at working with them as much as we can, and we'd really like to be able to bring existing applications along. So that's one thing I mentioned, code addresses. So like, file : line, or file : line : column, right? That output that tends to happen in all kinds of linter and compiler output and everything. So as soon as we can recognize those and sort of integrate those, make those as sort of messages to the rest of the system, then we've gifted all of those existing programs with, a little more interactivity. So that's really what we're trying to do. We're not trying to change too much, but like I said, if it was something like an editor, I would be nice if you could follow more existing conventions, maybe make it a little less scary. I think there's always going to be people that, fear change and don't want anything to be different.
Yeah, makes sense. So maybe just to follow up on you had a remark about IDEs, that there's a problem of interoperability and then plugins need to be redeveloped IDE. What came to my mind is language servers, which I think is an approach or maybe paradigm that's been getting more popular in the recent years, especially for syntax highlighting, debugging, that kind of stuff. Does that address this issue in any way?
Yeah, so I actually mentioned a language server protocol partway through there. So that's been really neat that that's been leveling the playing field for code completion, stuff like that. So it is something that we'd like to leverage, but it's not really the focus of our work.
Okay, then I would say, well, thanks very much again for your presentation, Michael, and an applause to you.
Thanks.
And next time you talk to Michele, please say hi on my behalf.
I will. Thanks.
Okay, then the final presentation is by Peter. So the screen is all yours.
Hopefully you can see my screen now.
Not yet.
Yeah, let me try sharing it again.
We still can see your video.
The screen sharing should work too. I just tried before the session.
Yeah, still just you.
Interesting.
So something may have changed in the last half an hour since you tried it out.
Yeah, I just tried to refresh the page. Just a moment.
Yeah, we've got time.
You'll just have to act it out.
I mean, without PPT, it also works. It's just a bit harder to understand. I guess you still can't see it, right?
No, we can still just see your video.
Yeah, not sure what the issue. We worked right before the presentation. How do you suggest we proceed?
Is it a kind of a PowerPoint presentation you're having?
Yeah, it's just a PDF.
Okay, maybe you can share the PDF with either Peter or Anas, where we know it did work, and maybe they have to run it for you. Because if you send it to me, we're running the risk of having the same issue.
Yeah, I just sent it to the chat. If one of you could share, that would be great. Apologies for the
That's okay.
inconvenience.
It's the Friday the 13th that I've jinxed.
Yeah, I guess.
The two of us are already in, whereas Peter and Anas were not.
Uploading the presentation.
Yeah, the joys of a live demo. There is always something that can throw a spanner in the works.
Still a lot of work to be done in IT.
Well, we've got another 28 minutes, so no rush.
That's weird. I actually we test the screen share before the presentation.
Yeah, it
Works fine at that time.
worked well before the presentation. I think I should share it in the chat. I don't know if. Sorry.
That's fine. On my end, I can't see anything yet.
Share the PDF in the chat. I'm not sure if one of you could maybe help open it.
Okay, yeah, it's there. So here we go. Great, thanks very much, Michael.
Yeah, thank you for
A
having
good
me.
old next slide, please. Will have to come. Okay.
I can finally get started. Thanks again, everyone, for the delay. So my name is Peter, and today I'll be presenting to you our work about parallel execution of blockchain transactions. Next slide, please.
Oh, one sec. Okay.
Thank you. So in blockchain systems, consensus, network, storage, and execution might all become bottlenecks when it comes to performance. Consensus has been addressed by some recent work, and we believe that out of these three hardware bottlenecks, execution is the hardest one to address, simply because in Ethereum and similar blockchain systems, transactions are executed serially. This work is to try to speed up execution through parallel execution without fundamentally changing the protocol. Next slide, please. So in our work, we actually identified two issues with parallel execution, and we proposed some solutions. So the first problem is that parallel execution on Ethereum seems to be severely bottlenecked. What we did is we ran a simulation using historical Ethereum dataset using 4, 8, 16 cores. And what we realized is the best case speed up that we could achieve was only 4 times, so much lower than expected. And the reason is that many blocks are bottlenecked on a chain of transactions that are conflicting or depend on each other. These can be traced back to applications like token transfers, decentralized finance, and games and collectibles. And if we take a closer look at the source of the contention, this usually conflicts on counters and arrays. Next slide, please. So we propose some techniques to eliminate these bottlenecks so that we can really use parallel execution. And the idea is that if you have a long chain of conflicting transactions, they conflict because they depend on each other. So what we want to do is we want to remove some dependencies so that we can cut this chain into multiple disjoint chains that can be executed in parallel with each other. So for token distributions, the case is that you would send many transactions from one sender to many receivers, and the sender balance would become the source of contention. We propose conflict-aware token distribution, which is simply put to use 2 or more sender addresses, and this way transactions from different senders can be executed in parallel, independent of each other. The second technique is more general. It's called partition counters. The idea here is that we could use counters that logically represent an integer, but under the hood, they represent 2 multiple variables or multiple storage locations. So if there are 2 concurrent transactions modifying the same counter, they might be operating on different underlying storage locations, and this way we could avoid conflict. And third, we also noticed that many operations, for instance, counter increments, are semantic commutative, so they could be reordered from the application's perspective, but this cannot be expressed on the virtual machine level because it's always compiled to a storage load and storage store operation, so there's a read-write conflict. We propose to extend the Ethereum virtual machine with commutative operations to address this issue. Next slide, please. In our evaluations, we found that assuming that we could apply these techniques to the majority of conflicts, we could drastically increase the parallelizability of the dataset, and it would actually converge to the optimum case when there is no dependency between the transactions. Next slide, please. The second problem that we identified is that of non-determinism. So in blockchain systems, determinism is very central because different nodes in the network need to be able to execute the same transaction dataset and reach the same result, reach consensus. But this is not always the case when it comes to parallel execution. As a motivating example, let's look at this diagram. So let's assume that transaction 3 depends on transaction 1. On node A, they are executed in the order of 1, 3. So 3 can simply commit because it sees all the writes by 1. But on node B, they are executed in the different. And as a result, transaction 3 needs to be aborted and re-executed. This kind of inconsistency or non-determinism between the nodes might become an issue in a blockchain setting. Next slide, please. So to address this issue, we propose a new scheduling algorithm called optimistic concurrency control with deterministic aborts, or OCCDA for short. And the basic idea is very simple. On node A, transaction 3, even though it could be committed in theory, we will forcibly abort it and re-execute it. Furthermore, this abort commit decision will be made prior to the execution of the dataset. This way, we can ensure that these abort commit decisions are made uniformly across all the nodes in the network, and we can reach higher level of consistency. Next slide, please. We also did some evaluation of OCCDA, and the expectation is that there is a performance impact with this forced abort of some transaction. And we found that indeed there is a performance impact, but on the data set observed, at least, this seems to be well within the acceptable range. So OCCDA might have a promising application in blockchains. Next slide, please. So to summarize our work, our goal was to work towards parallel execution of blockchain transactions, and we identified 2 main issues on the road to parallel execution. One is we have these bottleneck transaction dependency chains that limit the parallelizability of the dataset, and the other one is non-determinism. In our paper, we propose solutions to address these issues, and we hope that this can unlock further research towards parallel execution of blockchain transactions. Thank you very much for your time. I'm looking forward to your questions.
Thank you, Peter and Michael, for orchestrating the presentation. Do we have any specific questions from the audience? If not, then I have a couple of quick questions. So what you're suggesting, you add an additional abort, say in your case to, what was it, node A. What is the benefit of doing that? So what do you gain by having to re-execute your transaction 3 twice?
So here the idea is that the first execution of transaction 3 in this example should either be aborted on all the nodes or committed on all the nodes. And the reason is that in blockchain systems, there can be some penalty associated with aborts. So in the end, these abort commit decisions are part of the state machine. If we make different decisions on different nodes, then they will diverge and they will be unable to reach consensus. So there are 2 options here. We either, as I said, forcibly abort on node A, or we could delay the transaction of transaction 3 on node B to make sure that it can be committed.
Ultimately, do you, with that approach, would you execute that transaction multiple times on a particular node, or does that prevent it from starting in the first place?
So in our model, each transaction will be committed in the end. So if you can commit for the first time, then it's only executed once. Otherwise, it's executed multiple times.
Do you know what the, now I'm going a bit wide here. Do you know what the implications are with regards to energy consumption of that approach? Because blockchains are inherently known not to be terribly energy efficient.
For blockchains, that's an interesting question. The energy efficiency is usually not so much related to transaction execution, but more related to the consensus algorithm, especially proof of work, which is notoriously energy. Probably it's not fair to say inefficient. Some people argue it's efficient, but it uses a lot of energy. Transaction execution, I guess you could say it's wasteful because it's hugely redundant. All the nodes have to execute all the. But we argue our work is probably helping this issue by making transaction processing more efficient. So with the same hardware resources, you could take less time and potentially less energy. But this is not something we explicitly looked into, and this was not one of our goals. So to answer your question, I think this is less related to transaction execution and more related to consensus.
Okay. Do we have other questions from the audience?
This presentation, I didn't have time to cover the basics, and I think many people might not be familiar with blockchain. So if you're interested, please check out my longer presentation. That might help understand the setting.
Well, if we don't have any other questions, then we probably stop the session a bit earlier today. So thanks very much, Peter. And again, Michael, for helping out for that presentation. And on that note, I would say we'll conclude proceedings for now. There will be more sessions starting in about 15 or so minutes. So that gives us all time to have a drink or a bite to eat before we join the next set in about a quarter of an hour. So thanks everybody for attending. Again, thanks very much for the presenters, and enjoy the rest of ICSI. And for everybody, stay safe. Bye-bye.
Bye.
Have a good day.
You too. Thank you.